This presentation is about the turkey trap system. It is our 2020 senior project. Our group consists of 5 engineering students from different disciplines, all shown here. Our advisors are Dr. Bruce Dunn and Dr. Chirag Parikh. Our sponsor is the GVSU Biology Department of Natural Resource Management in conjunction with the Padnos College of Engineering and Computing School of Engineering. Here is a better view of our group. In the upper left corner we have Matthew Babb, a mechanical engineering major and our point of contact. Next to him we have Mason Cordes, who is an electrical engineering major. Then we have Robert Sebald, who is a product design and management engineering major. Below them in the lower left corner there is Catherine Seeger, who is a product design and management engineering major and our administrator. Lastly we have myself, Jonathan Swikowski, a computer engineering major and the project leader. I also appear in the upper right hand corner so you can tell who is narrating each slide. The GVSU Natural Resource Management Department does not have any current way of trapping and tagging turkeys, so the need for a safe, effective turkey trap has arisen. The information gained from the creation of this trap and the subsequent trapping of turkeys can be used by researchers at GVSU to predict turkey population growth and the stability of the turkey's ecosystem. Current products on the market are very expensive and can harm the turkeys. Therefore, there is a need for a cost-effective and time-saving solution to trap turkeys while ensuring the safety of the turkey during the tagging process. This turkey trap project has to adhere to the following specifications and constraints. Turkeys must not be harmed in the trapping process. The system must withstand Michigan nature. Quiet deployment so as not to scare the turkeys. Structure must be adjustable from 5 to 9 foot and 1 foot increments. The total system must weigh 200 pounds total. The system must collapse into a 6 by 3 by 2 foot volume. The system will accommodate a 25 by 25 foot net weighing up to 50 pounds. The deployment of the net from 100 feet away with a handheld remote, and the budget must not exceed $1,000.
Some of the commercially available solutions for capturing turkeys include rocket nets and drop nets. Rocket nets, while very compact, are loud when deployed and can be dangerous to turkeys who get hit by the fast-moving net or weighted edge. This risk of injury and startling noise are not ideal for the animal's welfare. Drop net systems, such as the Wildlife Capture Drop Net Kit, include an all-in-one drop net system with a silent drop because of the use of electromagnets. It has a large remote range of 200 yards and is available in the desired 25 foot by 25 foot net size. However, it is very costly, at almost $4,000 retail price, which doesn't even include the 12-volt batteries needed. This system is too costly for the benefits desired by our sponsor.
I will now discuss the turkey trap design. Now, because there are no commercially available products which meet our sponsor specifications, a new drop net system was designed. The new turkey trap system includes 4 adjustable low-carbon steel posts, all with stainless steel bases, as well as 4 12-volt batteries, 4 electromagnet release mechanisms, 4 RF receivers, and 1 RF transmitter. This allows for 4 individual post systems. Now the figure on the right shows the 4-post system with the net strung between the posts. Now, as I said before, the structure of the system was designed so that there are 4 individual post systems, one on each corner of the net, and each one of these posts can be seen on the figure to the right. Now this allows for configurability based on net size, so each structure will hold the electromagnets as well as the control box for each corner of the net. This allows for 4 individual post systems without wires connecting any of the posts. Now the structure of the system for one corner includes 2 posts, a stationary post which will be secured to the base, and a sliding post which will be used for height adjustments. Now both the stationary and sliding posts will be manufactured out of square tube. The square tube offered advantages over other cross sections such as round tube, and that the flat surfaces offer common mounting techniques such as the use of L brackets. Now the stationary post will be 1-inch square tube, while the sliding post will be 1.25 inch square tube. And then this different size allows for the telescoping action. And this also creates the height adjustability as well as makes transportation and storage more efficient because they collapse inside one another. Now the stationary and sliding post will be manufactured out of A513 low carbon steel. So now the base of the system will secure the structure post to the ground, providing stability needed to hold the weight of the net. So the base will be made out of 1.25 inch square tube at 2.5 feet in length and will be pounded into the ground and will accept the stationary post inside of it. The base will be manufactured out of 304 stainless steel. This is because the base comes into contact with the most corrosive environment, so a material used to provide more corrosion resistance will be used. Now I will go into detail on how the posts will be connected, how the height will be adjusted, as well as the mounting features used for the electromagnet housing and the control box. So the stationary post, which is the post on the left side of the images, will have 5/8 inch holes drilled every 6 inches, while the sliding post, which is the middle image, will have one set of 5/8 inch holes drilled at the base. And this allows for the height adjustment of the sliding post over the stationary post to achieve the required height range of 5 to 9 feet. Safety pins will be used to secure the stationary post and sliding post together, as well as to secure the stationary post to the base post. The image of the safety pin can be seen on the bottom of the slide. This was chosen over nuts and bolts just because they are simple and more efficient to use and don't require the use of tools. Now additionally, the sliding post will offer handles at the base to aid in the lifting of the sliding post over the stationary post. And lastly, the sliding post will include the welded L brackets. In total, there are 4 L brackets that will be welded to the sliding post and be used to bolt down the electromagnet control housing.
I will now be talking about the release method and the enclosure design. To ensure the turkey trap system meets the specifications mentioned earlier, an electromagnet was chosen as our method of releasing the net. Using an electromagnet allows the system to release the net silently and is capable of holding the designated net. To house the electromagnet, we have decided to 3D print an enclosure. By using 3D printing as our means to producing the enclosure, we are capable of creating more complex geometries, minimizing the time to manufacture it, reduce overall waste material, and it's relatively inexpensive compared to machining. Additionally, to ensure that the enclosure is waterproof, the bottom portion of the enclosure is designed to have a raised lip around the exterior while the top portion has a recessed pocket. This provides inherent waterproofing since water would have to travel up over the lip to get inside. The armature plate assembly is the part where the net attaches to. A carabiner will be used in conjunction with the assembly to allow the user to easily attach a net. Per the recommendation of the manufacturer, a nickel-plated steel disc will be used. This ensures that there is full contact between the disc and the face of the electromagnet, which promotes the strongest level of magnetic attraction. We decided to use JB Weld as our epoxy to secure the plated disc to the armature assembly. We considered other methods such as welding, but that raises additional issues. We would need to machine the assembly out of a ferrous metal, which would add weight to the system and could potentially harm a wild turkey if it were to fall on one. Additionally, the plating of the disc would need to be removed on one of the faces to allow for proper welding penetration, which may affect the magnetic attraction to the electromagnet. Finally, welding has the potential to warp the disc because of its thickness, which may also affect those magnetic properties. Lastly, the pin that runs through the assembly will be used to hold the assembly in place while the system is not receiving power. On the day of planned trapping, the user would remove the locking pin once the system has power, allowing the net to fall once the electromagnets are de-energized.
This is the RF control system. It consists of an RF receiver, a 12-volt relay, and an RF transmitter. The electromagnet will be the load in the system with its negative lead running through the relay at port 2 and its positive lead being attached to the positive terminal of the battery. When the system is active, the relay will be closed and providing power to the electromagnet. When the user wants to drop the net, they will press the button on the RF transmitter. This will send out a 433 MHz signal that will be picked up by all 4 RF receivers. Then all 4 relays will become open, taking power away from the electromagnets, dropping the net.
So at the end of our design phase, our workflow was unfortunately interrupted by the coronavirus pandemic. Because of this new hurdle, we were faced with several hard choices going into the build semester. The very first problem was funding from Grand Valley because we were pulling money from a Grand Valley grant. The grant was put on hold during the first tumultuous months of the pandemic, and when the dust finally settled, the full grant was no longer available for use by the team, only a portion. So choices had to be made about how to get as close as possible to the intended solution with the amount of money that we were allotted, the reduced amount that we were allotted. After much deliberation, we concluded that the EM boxes, the top here, and the RF control units were the most critical for function, and the support posts could be created at a later date. Detailed instructions of how to build these post assemblies were also given so that when the funds finally do become available, it will be very easy to complete this project. Another really unintended consequence of the coronavirus was not being able to physically get together to work on this project. This meant that we had to work really hard on staggering the work and making sure that each portion of the work was individual while also equally distributing it among the members. So we spent quite a bit of time organizing. You can see the Gantt chart that we created below about how to pass items back and forth, and how to move materials to each other safely and expediently, so that we weren't wasting time, but we weren't also risking the safety of others, especially with several of our members moving away from the Grand Rapids area because of the pandemic. It further complicated things. Testing was also limited because the full system was not developed. We didn't have the time nor the pieces required to do a number of the testing procedures that we would have liked to have done to make sure that this system is fully robust for the things that we want it to do. In order to have the EM boxes, the Electromagnet boxes, fully assembled and wired and put together. Testing was done on each of these receiver boxes here to make sure that they were all paired correctly and working in tandem, and then we were ready to do final assembly and testing of the full system that we were able to create. So with the final delivered design, we all gathered at our common meeting point, which just happened to be my garage outside of my house here, and following proper procedures, we got together and did some preliminary testing of our delivered design. We can play the video here. So as you can see in the yellow shirt very far away there, is one of our members, Mason. He's approximately 250 feet away and drops the Electromagnet receiver with very little trouble at all. And you can also see from that video that this was able to hold up that 8-pound brick very easily, and we were able to do quite a bit more weight with it as well, proving that our intended weight load expected from the net will be perfectly fine with our system. So here's just a quick summary of some of the verifications that we did to make sure that from what we delivered, we were following sponsors' critical specifications. In the calculations and simulations that we've done, which we've done several, we made sure that the battery life on those RF receiver units are acceptable, that the stress felt by the Electromagnet box and the mounting procedures don't go over any kind of tolerance for both regular and fatigue failure using ANSYS software. We did an RF distance test live with a finished box, and we're able to get 300+ feet more than the minimum spec in triggerable distance, which is beyond what the sponsor would ever need. We did strength testing, as you saw in the video. We had bricks tied up, and the electromagnet box was able to handily support up to and above 300 newtons of applied force. 300 newtons was the maximum that we were able to test ourselves. We did some sound testing, and all noises from the electromagnet box and the RF control unit were well below audible while running and when actuating, which was super important to make sure that the turkeys can't hear the sound of the net dropping until it is already on top of them.
There were two main challenges that were overcome when completing this project. The first being the manufacturing technique of 3D printing the electromagnet enclosure, and the second being the material selection for the structure. So now, while 3D printing is fast and readily available, it proved challenging to dial in the correct settings for the PETG material that was chosen. And this material was new to many of the people with 3D printers, which resulted in a learning curve to determine the optimum settings. Now, additionally, the electromagnet housings were very large prints, some up to 24 hours, which caused headache when prints failed midway through. And then lastly, because there were multiple iterations necessary on the printed components, it just resulted in extra time needing to print, making it hard to keep a consistent schedule, especially if there was a failed print. So something we did early on was just to make sure we budgeted more time for 3D printing. Now for the structure material, much thought was put into finding a strong enough material for outdoor conditions on a budget. With a substantial amount of material needed, providing an entire corrosion resistant surface wasn't really in the budget. So options like ABS, PVC, and aluminum were discussed, but were steered away from early in the designing process because they all have plastic fatiguing deformation characteristics. So as a compromise, a low carbon steel was chosen for the structure posts with a Rust-Oleum paint application to provide an indefinite corrosion resistant surface. And then a 304 stainless steel base post was used in the more corrosive environment. Now the base will be subject to ground moisture when it's in the ground and much more abrasion during the pounding and the insertion into the ground. So thus that a more corrosion resistant material was chosen to kind of mitigate that issue. Now that concludes our presentation. If you have any other questions or would like to talk further to the turkey trap team, please visit our Zoom meeting at 1 p.m. on Friday, July 31st. Thank you.